Well, hello everyone, and welcome to my talk about duplication graphs, especially its connected component, and the phenomena that a lot of people are interested in, power law, tales of degree distribution. My name is Krzysztof Turowski, and this is joint work with Philippe, Jacquet, and Wojciech Szpankowski. Unfortunately, we cannot meet in person, but I hope that this talk would be a good substitute of the introduction into this very interesting topic. First, what are the dynamic networks that we are talking about? That these actually fall into some very wide phenomena that we observe in the real world. Social networks, biological networks, such as protein-protein networks, brain networks, some internet connectivities that we have basically various ways in which networks, that is, graph-like structures that are evolving over time, may arise. Here we are interested in a very simple variant of that is, suppose that we have a certain fixed rule that we add one vertex at a time with some connections to previously existing vertices. What would happen? Which graphs we could generate? What happens in expected case? And in particular, we picked one quite known model going by name duplication divergence model, which is very straightforward in its definition. So we start from a certain graph on T0 vertices, and we add vertices one by one. When we first, we pick any vertex uniformly at random from the existing graph, we add a new vertex, and then for each vertex adjacent to the picked vertex, which we call the parent V vertex, we connect this neighbor of V to U by throwing a coin toss with probability P independently at random. And we repeat that for all the neighbors of V. In this way, U probably gets connected to some neighbors of V. We obtain a new graph, and we may repeat this process until we reach T vertices. We call this model duplication divergence, and we denote it by dd of T of P, where here we just assumed in the background that graph G has a certain starting point. This model is supposed to be well suited to many types of biological networks. Especially it was underlined that this mechanism clearly resembles the causal mechanism which can be observed for protein-protein networks, in which, because we may view it in the other way, that we copy vertex U from vertex V, and we remove one by one independently at random the edges with probability 1 minus P. So that is why the name duplication divergence goes. And it is supposed that in proteins, it works more or less in that way. Of course, it has been tried with many other models with certain degree of success, and it's really interesting and worth pursuing path to check whether these networks really are going according to this model. But as for now, we are interested in pure theory. That if we look at the example, suppose that we start from this graph G, we have set P to 0.8, and we pick uniformly at random. And it happens so that we picked vertex U2. So we add vertex V1, which is a copy of U2. So we pick all the neighbors one by one of U2, U1, U3, U6, and for each, we toy in a cost with probability P. In this case, it happens so that all the edges from U2 to its neighbors were copied, and now there exists as a vertices of the vertex V1 to the neighborhood of U2. But we may repeat this step, and suppose that now we pick vertex U1, and U1 has two neighbors, V1 and U2, and we toss a coin twice, and for V1, it happens so that we do not create an edge, so this event with probability 0.2 happened, and from V2 to U2, it happens so that there is an edge. And we may repeat that. For example, we may pick V1 now, picking vertices uniformly at random, and we may copy certain edges to obtain V3. Note that in this case, V3, if we look just at the static graph, it may be obtained from V1, so V1 may be picked as a parent of V3, or U2 may be picked as a parent of V3. And these are both eligible constructions. However, with different probabilities, because of course, if we copy V3 from V1, there has to be 3 coin tosses. 2 of them has to be successful. And if, in the case that we copy V3 from U2, it has to be 4 coin tosses, as U2 has 4 neighbors, and only 2 of them has to be successful. Okay, but suppose we now understand what the model is about, what we may do. The basic parameter that probably all theorists interested in random graph theory are interested is the degree distribution. So suppose that we fix a number k, and we look at the graph as the number of vertices goes to infinity, and we ask the question, what is the fraction of vertices, the expected fraction of vertices in such a graph that has degree exact k? And it turns out that this number we denote by f of k, and in this model there is certain work that was done previously. Hermann and Pfaffelhuber proved that for any k greater than 0, this fraction of vertices goes to 0 as n goes to infinity. So actually, if we pick randomly, that we would we cannot hit with any positive probability any vertex of fixed degree k. Moreover, if we look at the isolated vertices, if p is small enough, it is less than 0.67, and so that we get that almost all vertices are isolated. That is, the probability that the fraction of vertices which are isolated tend to 1. Otherwise, it tends to some constant value between 0 and 1. Lee and others looked one step further into this issue. So they investigated the number of vertices of degree 1 in this model, and they concluded that the fraction decreases, but not faster than logarithm of t over t. So from Hermann and Pfaffelhuber, we know that it cannot decrease, it cannot tend to a constant, so it goes to 0. But the question is still open, how fast it decreases to 0. And of course, for other degrees, nothing is known actually. What we may study more, that other work includes studying average degree, expected number of triangles, number of open triangles, maximum degree, number of automorphisms in this model. And there is some work to be, which was done, and some work to be done. But this time we were concentrated still on the degree distribution. However, as we see from Hermann and Pfaffelhuber work, especially asking here for this model the question about power law phenomena can be answered straightforwardly in negative, because we know that for all degrees greater than 0, it is 0. So we have no power law phenomena, even no exponential decay. It is just tending to 0. The question is, what we have if we concentrate only on the connected component of the graph. So we generate graph on n vertices, we discard all isolated vertices, and then we compute fractions for these. So an of k denotes the fraction of the vertices of degree k in a connected component of the duplication divergence graph. Observe that any duplication divergence graph would have only one connected component. As the new vertex, if the new vertex which is attached is isolated, it stays isolated forever. And if it is connected to a already existing connected component, that it remains connected to this single connected component throughout the rest of the generation process. Okay. Now that our point of departure, so the theorem by Jordan, who said that, and proved actually, that if p is less than e to the minus 1, there exists a certain constant beta which depends only on p, and is a non-trivial solution of this equation, then actually it is the case that we have a power law phenomena. So A of k as k goes to infinity is proportional to the k to the minus q. So k to the minus beta, in the sense that if q is less than beta, then we tend to 0, and if q is greater than beta, then we go to infinity. So this is almost power law behavior. There is a question whether if we have A of k and we have q equals to beta, whether it is the limit is a constant, non-zero constant, or whether it contains some, for example, logarithmic or polylogarithmic factors depending on k. We close this gap. We provide the exact limit of this expression. And how do we do it? First, it's necessary to introduce Jordan's approach. Jordan basically took this generation process and turned it into continuous time Markov chain, constructed the generator of this Markov chain over the space of all integers, and then tied this stationary distribution of quasi-stationary distribution to this generator as a left eigenvector of subset of Q for some eigenvalue lambda. And this allowed him to form this equation that we see below. And here, from here on, it is just was just a matter of technique that we may go to generating functions we all know and cherish, and we may solve this equation. That the equation above that we introduced implies that for 0 we have starting point 0, and Jordan also has shown that if the derivative of a in 1 is finite, then a of 1 minus p is indeed a constant, because a of 1 by definition is sum of all ak's, and since ak's are fractions of vertices of degree k in a connected component, a of 1 is less or equal than 1, so a of 1 minus p is definitely constant. And then if it is non-zero and finite, then actually we can find the eigenvalue on which depends, and we may even simplify this equation further. And basically what Jordan did from that on was to show that this quasi-stationary distribution has the cube moment or hasn't the cube moment. And depending on for which values of q it has the moment or not, this implied whether the actually the tail was heavier or lighter than, and that the limit really existed, tended to 0, tended to infinity. And that, of course, implied his result. We went quite differently. So we basically took the Jordan equation, and we asked, using various analytic methods such as Mellin transform, can we extract the limit of a of k over k to the beta? And we found it. Although the expression is quite convoluted, we know that there are only several values and functions. There is b, there is beta, which we know that it is constant dependent on JP. There is Euler gamma function, and there are two functions which are denoted as d and e, which also has this quite convoluted form, but nevertheless they evaluate for this value for any constant s. Function d evaluates to some constant, and the value of this first expression, that is 1 over e of 1 minus e of infinity, also evaluates to some constant. And to give you a glimpse of that, we provide also the figures for that, and we see that for all ranges that there is no problem actually, and we see that as p approaches e to the minus 1, then the values for some of the parameters really go up to infinity. So okay, we started by writing down the Jordan's equation, and we wanted to solve it. So the first thing we did was to manipulate the variables and the functions, and we obtained the function in the second line, so the function in C, which is basically expressing that the C of W over P is a linear combination of C of W, of the C prime of W, plus some constant. Unfortunately, the boundary conditions that we got were for C of infinity, which is fine, and for C of 1, which is actually problematic in that sense that as Mellin transform we know would require the boundary conditions to be in 0 in infinity. Therefore, we did a trick, and the trick was as following. Suppose that we have the same equation, only the constant at the end is different. And suppose that we have that it's indeed it has some Mellin transform, and this Mellin transform exists in some fundamental strip. Then we may quite easily translate between E and C using the equation at the bottom of the slide. So it's no problem. So the only problem is how to solve this equation in E and how to find the constant K. So we first guessed the equation for the Mellin transform of E, denoted by E star. And it turns out that this equation, if we look at it, it has only simple isolated poles of 3 types. First, there are non-positive integers, which are poles that are introduced by gamma function. Second, we see that we have here the function in the denominator that is the product. And this product, each part of this product has 2 roots. One is for the positive integers, and one is the positive integers plus some non-trivial real solution of this equation p to the s plus s minus 1 equals 0. And these are non-overlapping. This is some value between 0 and 1, as it turns out, for the range of p that we are interested in. And therefore, we know that we have these evenly spaced poles for all integers, and we have from 1 to 3 that we have certain poles between them. Yet the crucial part is that, for example, between -1 and 0, there is no other pole. So this was probably the core of our work, to prove that if S has the real value between -1 and 0, and P is in the range that we are interested in, 1 over the absolute value D of S is absolutely convergent. And we prove that, and to support that, we provide the chart of values for T, where T is the imaginary part. And we see that although it behaves, the swings can be very wide, that actually it goes quite smoothly to 0 when T goes to either -infinity or +infinity. And we provide a formal proof in the paper. So we have this already done, and next step was to show the recurrence equation for E star of S. By simple substitution, we show the following equation holds, and also we may provide a basic reverse Mellin integral. And after integration, we get the following formula. The only problem was that how to pick C, but indeed it is sufficient that C has to be in some fundamental strip, and we know that between -1 and 0, we have the fundamental strip, so we have no poles whatsoever in there. And then we may proceed to show that the extreme values may be found by Cauchy residue theorem, and similarly, we may find the value of the E of infinity minus E of 1 for some value between 0 and 1. And of course, here we also, all the values are, here we also have some fundamental strip, and there is no problem for that. That's both values exist, since this value has to be finite too. Okay, but now with the approximation, we have to use the Cauchy residue theorem, as probably was used hundreds of times before. So we need to draw a rectangle, which will have the left side somewhere in the fundamental strip between 0 and -1. The upper and lower part will go eventually to plus and minus infinity in the on the imaginary axis. And we go on the right side as far as we want, how many terms and how good the approximation we want. And we put here on the figure the example integration area for m equals to 2.5 and s star equals to 0.7, right? So we see that we hit 4 poles within this integration area. Okay, so we proceed using residue theorem and using the transformation between E and C. And putting them together, we may write that C of W is a sum of certain quantities which are directly dependent on the residues of function E star at the poles. So at 0, at 1, at 2, S star plus 1, plus some remainder. So now there is the question how to solve these residues. And these residues are actually straightforward. That if we have this expression for E star, which we proved, that we just apply basic tools, and we may obtain value for each of them. And in each case, we obtained that this is indeed some finite value. Plus, we can prove that the remainder also behaves like some big O of W to minus M. So putting this together, we got some large expression which depends on some non-positive powers of W. So this is a polynomial in non-positive powers of W. Now, going from C to A, we need to go from W to Z. And since W was defined as 1 minus Z to the minus 1, we go from a polynomial in negative powers of W to the polynomial in positive powers of 1 minus Z. Okay. So if the part is 1 minus z to some power alpha, which is a positive integer, then it is straightforward. This is a polynomial. This does contribute to asymptotics of A of z. If it is real, then we use Flageolet or least-count transfer theorem, and we may find exactly what the value of the coefficient standing next to the z to the k is. And of course, we have some big O approximation of lower order terms. Similarly, if we want only some big O approximation, that the transfer theorem holds as well. And now it is a matter of just putting all these together, and we obtain the final result, the big result, in which indeed all the parts are constant. And since we have only a finite number of big and small O's, that we obtain some tail which grows smaller than the main part. And this gives us the final result. So the case when P is greater or equal than e to the minus 1 remains open, we conjecture that there begins some dependency of n. That here we have only dependence that A of n grew like k to some power. We conjecture that ultimately it starts to depend on n to some power of alpha, but this remains to be solved. Thank you very much.